Have you ever noticed how AI, for all its intelligence, can be a bit inflexible? Like you show it something completely new, something it hasn't seen before, and it just doesn't know what to do. It's like it's stuck in its ways. Well, today, we're diving into a really fascinating area of research that's trying to change that. It's all about helping AI to learn and adapt on the fly, even in the real world, when it encounters the unexpected.
That's the challenge, right? Most AI models, they're trained on these carefully curated data sets, and they learn to recognize a very specific set of categories. But the real world, it throws curveballs. It's constantly presenting new things, new types of data. So how do we equip AI to identify these entirely new categories, especially when it's out there in the wild, actually being used? This is what's often called class shift, and it's a major obstacle for a lot of current AI systems.
That's like AI needs to break free from the textbook and learn to think on its feet.
Exactly.
So, to help us understand how researchers are tackling this challenge, we're looking at a paper titled Test Time Discovery via Hashing Memory. Now, I know the title might sound a bit technical, but the idea behind it is quite elegant.
It is.
So let's jump right in.
Okay.
What is test time discovery, or TTD? Can you explain it in simple terms?
Imagine you've trained an AI to recognize different dog breeds, let's say golden retrievers and Siamese cats. Those are its known categories, right?
Right.
Now, out in the real world, it encounters, let's say, a border collie or a Persian cat, breeds it hasn't specifically been trained on.
Okay.
A TTD-capable model needs to do two things simultaneously. It needs to correctly classify the golden retrievers and the Siamese cats, the ones it already knows,
Hmm.
but it also has to recognize that these new breeds, the border collie and the Persian, they represent new, previously unseen categories.
So it's not just about getting the familiar stuff right.
Right.
It's also about being able to say, hey, this is something entirely new. I haven't encountered this before.
That's a great way to put it. The paper actually uses a nice visual in Figure 1A to illustrate this. Training on some common pets, then testing on those, plus some less common animals.
That makes sense. Now, this sounds a bit different from something I've heard of called test time training, or TTT. What's the distinction there?
TTT is more about adapting a pre-trained AI to changes in the style or the environment of the data, but usually the categories themselves, those remain fixed. For example, if you have an image recognition model that was trained on these high-resolution, studio-quality images, and then it's deployed in a setting where it's seeing images from a security camera, grainy, low-light images, TTT helps it adjust to that change in image quality. But it's still looking for the same things, dogs, cats, cars, whatever it was trained on. TTD, on the other hand, is specifically about recognizing entirely new categories of things.
So TTT is like adjusting to a new setting, a new environment, while TTD is about recognizing new objects or concepts altogether.
Exactly.
Okay, now what about novel category discovery, or NCD? How is that different from TTD?
NCD also focuses on identifying new categories, but the key difference is in the timing and the setting. NCD typically happens offline after you've collected a data set. It's about analyzing this pile of unlabeled data and trying to group similar items together into what might be new categories.
Okay.
It's like you have this box of, I don't know, various tools, and you're trying to sort them into different types based on their features. That's useful for understanding a data set you've already gathered, but it's not ideal for situations where you need to recognize something new in real time as it's happening.
Like in the moment.
Right. TTD is designed for those real-time, in-the-moment scenarios.
That makes sense. So TTD is the ability to recognize something new on the spot as it happens.
Precisely.
Now, can you give us some real-world examples where this kind of capability would be really valuable, really game-changing?
Absolutely. Let's think about healthcare. Imagine an AI diagnostic tool that's trained on images of known diseases. If a new kind of virus emerges or a new form of cancer that hasn't been seen before, a TTD-enabled system could flag that as something unusual, something potentially new, alerting doctors to this potential new threat.
That's crucial.
Another example is in the field of autonomous robots. They're often trained to navigate based on recognizing common objects, people, cars, obstacles. But what if a robot encounters something completely unexpected in its environment? Maybe a piece of equipment it's never seen before, or as the paper mentions, livestock wandering onto the road. A TTD system could identify this as a novel entity even if it doesn't have a specific label for it, and that would allow the robot to react cautiously and safely.
So it's all about handling those unexpected situations, those things that weren't in the textbook, so to speak.
Right.
Now, what makes TTD such a difficult problem to solve? What are the key challenges here?
There are several. First, it's incredibly difficult to distinguish between something that's truly a new category and something that's just a variation of a known category. Going back to our dog breed example, if the AI sees a Yorkshire Terrier for the first time, is that a new category of animal?
Hmm.
Or is it just a breed of dog it hasn't seen before? That distinction with limited information is a really tough one to make.
It's like trying to decide if you've discovered a new species of bird or just a bird with unusual plumage.
Exactly. And Figure 1b in the paper highlights the difficulty of knowing how to categorize something new when you only have a little information about it.
Okay, so that's one challenge. What's another?
Another challenge is that even when a potential new category is identified, we usually only have a handful of initial examples. It's like trying to learn a new language from just a few phrases. It can easily lead to overfitting, where the AI learns those specific examples too well and doesn't generalize to other instances of the sum category. Or it can lead to underfitting, where it just doesn't learn enough to properly distinguish the new category from other things.
So it's like learning from a very small sample size.
Right.
Okay, so that's two challenges. What's the third one?
The third major challenge is what's called catastrophic forgetting. This is a common problem in AI where learning new information can cause the model to forget what it's learned previously. So as the AI is trying to learn about these new categories, it might start to perform worse on the categories it was initially trained on.
So it's like the more it learns, the more it forgets.
In a way, yes. It's a delicate balancing act. The paper mentions that some traditional methods use a thresholding approach. If the AI isn't very confident in its classification, it might just label the input as new. But Figure 2a shows how this often leads to confusion between different unknown categories. The boundaries are blurry, and it makes a lot of mistakes.
So we've got these three major challenges: telling new things from variations, learning from limited data, and preventing forgetting. That sounds pretty daunting. So how does this hashing memory approach try to address these challenges?
This is where it gets really interesting. The paper proposes this clever, training-free mechanism called hashing memory, or HM for short. The idea is to enhance both the AI's regular predictions and its ability to discover new classes by comparing the current input, like an image, with a collection of past inputs that are stored in what they call a memory buffer. And the key to this efficient comparison is using locality-sensitive hashing, or LSH.
LSH. Can you unpack that a little?
Think of LSH as a really fast way for the AI to say these two things are kind of alike without having to do a detailed comparison every single time. It's like having a shortcut to find similar items.
It's okay.
Imagine you have this massive library, right? And you want to find books that are on similar topics. Instead of reading the summary of every single book, you could use a system where books with similar keywords or themes are grouped together on the same shelves. LSH is kind of like it creates these groupings of similar data points.
So it's like a way to organize the data to make comparisons much faster.
Exactly. Now, the specific hashing function they use in this paper, which you can see in equation 1, it looks at two main aspects of the features that are extracted from an image: the magnitude, or the norm, and the direction. You can think of the norm as how strong or prominent the features are, and the direction is like the pattern of those features in a multidimensional space.
Okay.
They simplify the norm into a few discrete levels and then compare the direction against a set of randomly chosen reference directions. If a new image has a similar norm and its direction aligns with the same reference directions as an image already in memory, they're likely to end up in the same bucket.
So similar strength and pointing in roughly the same direction. Got it. Now, what about these memory buffers you mentioned? How do they work?
They use two separate memory buffers. One, called mknown, stores examples from the known classes, the ones the AI was initially trained on. The other, munknown, is where the AI stores examples that it identifies as potentially belonging to new unknown classes during the testing phase.
Okay, so one for what we know and one for what we're discovering.
Exactly. Each buffer has a fixed capacity. It can only hold a certain number of examples per class. And to keep the munknown buffer up to date as new data comes in, they use a technique called reservoir sampling. It's a way to ensure that the buffer maintains a diverse and representative set of examples from the encountered unknown classes.
So it's like dynamically updating our collection of unknowns.
Right.
Now, how does this whole LSH system actually help with prediction and discovery?
When a new image comes in, the system calculates its hash value using that norm and direction method we talked about.
Right.
Then it looks at the corresponding hash bucket, which is the group of images that have the same hash value. You can see that in equation 3. If that bucket is empty, or if it only has a few images in it, it means that this new image is potentially something novel. something from a new class. So it assigns it a new temporary label, like in equation 4, and stores it in the unknown buffer.
So an empty bucket is a potential new discovery. What if the bucket isn't empty?
If there are other images in the bucket, the system compares the new image to those images and uses a voting mechanism. The class that has the most images in that bucket becomes the predicted class for the new image. If there's a tie, it picks the class whose images in the bucket are, on average, most similar to the new image.
So it's like checking for the most popular label among similar images.
Right.
Now, the paper also mentioned something called graph neighbor searching. What's that about?
That's a way to make the predictions more robust. You see, relying on a single hash bucket can be a bit risky because hashing is approximate. So they propose thinking of these hash buckets as nodes in a graph. The connections between these nodes, or edges, represent how similar the buckets are to each other based on the average direction of the images within them. Then, for a new image, the system not only considers its initial hash bucket, but also looks at the top KIM most similar neighboring buckets. It's like getting a second opinion.
So it's not just about the immediate neighbors, but also about the broader neighborhood.
Exactly. And to further improve things, they have this global to local classification strategy. They first use a more general classifier that's learned prototypes or representative features of all the known classes and previously discovered classes. If this global classifier is very confident in its prediction, it just goes with that. But if it's not very confident, meaning the new image might be something unusual, it then switches to the more detailed LSH-based classifier to see if it matches any of the specific past images in the memory or if it represents a completely new class.
So it's like a two-step process. First, a general check, then a more detailed investigation if needed.
Exactly. And for the prototypes of the discovered classes, the ones in unknown, they use an exponential moving average, or EM, to update them as new images come in. Equation 6 shows you that.
Yeah.
But importantly, to prevent forgetting, the prototypes for the known classes, the ones the AI was initially trained on, those are not updated.
So keep the core knowledge intact.
Right.
Now, the paper also talked about a memory self-correction mechanism. What's that all about?
That's a really clever way to improve the accuracy of the memory over time. The labels initially assigned to the new classes are essentially guesses, what they call pseudo-labels, and they might not always be right.
Initial guesses can be wrong, yeah.
Exactly. So this self-correction mechanism outlined in equation 7 periodically selects a small portion of the images in the unknown buffer, ignores their current labels, and then uses the LSH-based classification to relabel them based on their most similar neighbors in the entire memory, including both the known and unknown classes.
It's like double-checking its work.
Exactly. If an image is relabeled as belonging to a known class, or if its new label is from an unknown class that's already full in the memory, it's removed from the buffer, which helps to keep the memory focused on the truly novel and underrepresented categories.
So it's like refining the memory, making it more accurate.
Right.
Now, how did this whole system actually perform in their experiments? What kind of evidence did they provide?
They tested their approach on 3 standard image datasets: CIFAR 100D, CUB 200D, and Tiny ImageNet-D. These are commonly used benchmarks in computer vision, but they modified them specifically for the TTD task.
Okay.
Table 1 in the paper compares their hashing memory method to several other methods, including simply techniques that use thresholding, as well as some more recent methods that require additional training during the test phase. And what they found is that their HM method outperformed all the other methods across all 3 datasets in both real-time and post-evaluation scenarios. It was better at identifying novel classes and also better at maintaining performance on the known classes with less forgetting.
That's really impressive.
They also found something really interesting, which is that the methods that involved training during the test phase actually suffered a drop in performance. It seems like trying to continuously update the model as new classes are discovered can actually make things worse in this TTD setting.
So sometimes less is more.
It seems so.
What about the number of potential new classes? Did they look at how that affects performance?
Yes, in Table 2, they explored that. They found that allowing for more potential new classes can initially improve the ability to detect novel things. But if you set that expectation too high, it can actually hurt performance and lead to more forgetting. So there's a sweet spot there.
A balance to strike.
Right. And they also compared their method to some standard novel category discovery metrics, shown in Figure 4 and Table 4. Even under those more traditional evaluations, HM performed very well, showing that it's a robust approach.
That's good to know. They also did some experiments with human labeling versus automatic labeling, right?
Yes, in Table 3A. They found that human labeling did improve the accuracy of the labels in the memory, but it didn't necessarily lead to a big improvement in the overall classification performance.
Interesting. So human input helps, but it's not a magic bullet.
Right. And Table 3B was particularly insightful. They found that if they allowed the model to be trained during testing, even while using the hashing memory, it actually performed worse. This suggests that keeping the core model fixed is really important for TTD.
So again, avoid retraining.
Yes.
Did they look at the impact of memory size and the self-correction mechanism?
They did. Table 4 showed that a very large memory can actually hinder the rediscovery of new classes, so there's an optimal size there. And Figure 5 beautifully illustrated the effectiveness of the self-correction mechanism, showing how it cleans up errors in the memory over time.
Making the memory more reliable.
Exactly. They also looked at the frequency of self-correction in Figure 6, finding that there's a sweet spot there as well, not too often, not too infrequent.
Timing is key.
It is. And Table 5 showed that both the hashing memory and the self-correction mechanism were essential for the performance improvements they observed. They also included some visualizations like the TSNE plot in Figure 7, which shows how well HM separates known and unknown classes and groups, similar images together.
So the visual evidence supports their findings.
Yes.
Okay, to wrap things up, what's the big takeaway from all of this? Why is this test time discovery research so important?
It's a significant step towards more adaptable and robust AI systems. Systems that can handle the open world, the unexpected. It's about moving beyond the limitations of traditional AI that assumes a fixed set of categories and allowing AI to continuously learn and evolve.
And the key innovation here seems to be this training-free, hash-based memory mechanism.
Precisely. It's a clever way to discover new categories efficiently without the need for constant retraining.
The paper did mention a couple of limitations, though. What were those?
They acknowledge that storing test data could raise privacy concerns in certain applications. And they also suggested that there might be even better hashing strategies out there that could be explored in future research.
So there's always room for improvement, but it's definitely a promising direction.
Absolutely.
So what's the final thought you want to leave our listeners with?
Imagine the possibilities if AI could truly learn on the fly without the need for retraining every time it encounters something new. How would that change fields like medicine, environmental monitoring, or even our daily lives? What other areas could benefit from AI that can genuinely discover the unknown?
That's a really thought-provoking question. If you want to learn more about this research, you can find a link to the paper in our show notes. The researchers have also made their code publicly available, and we'll include a link to that as well.
It's definitely worth checking out.
Thanks for joining us for this deep dive. It's been a fascinating exploration.
It has. Thanks for having me.